Okay, so here goes part 2 of the notes. So this one is about the intersection of polar curves. Because when you graph something, if you graph it on your calculator and go from 0 to 360 for your theta step under the polar, you'll notice that it's drawing the graph as it's going through the different angles. And so even though when it's done, if you superimpose two polar graphs, it looks like they intersect at various places, the true intersection is when they hit the same place at the same theta value. So what we're going to do is develop a way to figure out what are the true intersection of the two curves. Okay? So the first thing we're going to do is we're going to graph these two polar graphs on the same grid and see what they look like. So here we have a circle that has been reflected over the polar axis with a diameter 4, so 1, 2, 3, 4, coming through the origin, so it would look something like that. And we have a cardioid, since A equals B. It is also going to be reflected on the other side, so A plus B is 4, so it looks like there's an intersection there. A minus B is 0. We know the sides will go out to 2 and at 272, and the graph will look something like this. Okay, well, I kind of missed that other spot there. Let's draw this a little better. Let's try and come out like this, hit that spot, and come out. Okay, there we go. So there's a graph. It looks from this vantage point, when you're all done, that maybe there are at least two intersection points. So let's first now go and solve it algebraically to see algebraically what might be the case. So we have -4 cosine theta equals 2 minus 2 cosine theta. And we can bring everything over to one side so that I have 0 equals 2 plus 2 cosine theta. And actually now I'm going to bring this 2 over here, divide by 2. So we're solving when cosine theta equals a -1, and that solution is only going to be at 180 degrees. So the true solution, it seems, is only going to be over here. All right. So what's another way that we can truly tell? Because when you're just graphing them, if you weren't to do it algebraically, well, this is kind of cool. If I look at these two equations as rectangular equations and graph them on your traditional graph. So if I looked at y equals -4 cosine theta, and so that'd be y1, and y2 equals 2 minus 2 cosine theta. And let's look at what happens when we graph those. So we'll keep the first one in the blue. So that's got an amplitude of 4. So we're going to go up here to 4, down here to 4. It's going to be reflected upside down. It has no vertical shift. It's going to go out to 360. So let's mark up our graph. So once again, I'm going to be really picky about you labeling your axes. And so this one is going to start low, then hit the sinusoidal. It'll hit a high here, sinusoidal, go low. You thought you were done with trig graphing. You thought wrong. There we go. Okay, now let's graph your 2 minus 2 cosine theta. So that one has a vertical shift of 2 with an amplitude of 2. It's also going to be reflected. So it's going to start low at 90 degrees. It'll be on the sinusoidal. 180, it's going to hit the high. There's our intersection point. 270, it'll be here. And at 360, it hits its low again. So this one will look like this. And notice when you graph them, then the true intersection point actually happens. So what was actually happening at 0 is not happening at the exact same time, so it's not a true intersection point. So the only true intersection point we have is here. Okay, now notice that I was able to do that without touching a calculator. Sometimes you will find a calculator might be a little bit handy for some of these, but not necessarily for the algebraic. So let's take a look at how that would look. On this second equation, so I have here a limacon, and since 3 minus 2 is a positive 1, this is just a limacon with a dimple. So if I were to graph it, I know a plus b is going to be 5, but this is going to be sine, so it'll be up here on the y. 1, 2, 3, 4, 5. There's a plus b. And my sides are going to be out here at 3. That's when sine is 0. 1, 2, 3. And a minus b is out here at a positive 1. So this is going to come around. It's going to have a little dimple. And it's going to come around like that. Okay, so this is your limacon. And as we saw before, this one is going to be one of your conic sections. Since a is greater than b, think about when you square it, 9 minus that 4 is going to give you a positive squared term, so that's going to be an ellipse. And I'm not going to expect you to know how to necessarily, well, actually this one you can graph as a polar graph. It's not that bad. Doing it rectangularly on the other axis will be a little harder. So all we have to do is just plug in some values of theta. So if theta is 0 or 180, I'm going to be at 4/3, right? So 0, 4/3, that's a little bit past the 1, and a little bit past the 1. And then if I plug in 90, I'm going to have 4 over 5, so that'll be 4/5. So that'll be right before the 1, up at 90 degrees. And at 270, you have 3 minus 1. So this is going to come all the way out to 4. 1, 2, 3. And since we know it's an ellipse, you can kind of just sort of we're going to just kind of graph our I think I messed up on that part. Bring it around like that. That was not the best graph in the world. Let me try that. Clean that up a little bit. Okay. So basically we know we have an ellipse here. So it looks like we have 2 intersection points. So we can go ahead and find them algebraically. So I'm going to set 3 plus 2 sine theta equal to 4 over 3 plus 2 sine theta. And I can then cross multiply so that I have 3 plus 2 sine theta squared equals 4. So this is going to be 9 plus 6, 12 sine theta plus 4 sine squared theta equals 16. Looks like we have ourselves a quadratic. So let's see how this will be 4 sine squared theta. We're going to set it all equal to 0 plus 12 sine theta. And then 9 minus 16 is going to be I'm just double checking because I feel like I made a mistake somewhere. Why did I square the 16? Hello? Sorry, it's late. That should still just be 4. That's what my mistake was. Okay, so 9 minus 4 is going to be a 5. So this will be plus 5 equals 0. I was thinking before when you square the 2 sides. All right, so this actually is going to factor into 2 sine theta. 2 sine theta. That gives me my 4 sine squared theta. And my last term, well, the only factors you have of 5 are 5 and 1. And that works because if you do your little double rainbow, you get 10 plus 2, which gives you the middle term of 12. So setting these equal to 0, 2 sine theta plus 5 equals 0 says sine theta equals a negative 5 halves, which is greater than 1. So that won't give you any solutions. On this side, I'm going to get sine theta equals a negative 1 half. And we know that that is true when theta equals, I'm going to go back here. This should be 360. So that's true when theta is going to be 210 degrees and 330 degrees. And in this case, look at that on our graph. Spot on. Okay, so there's our two solutions. Now let's look at it rectangularly. So 3 plus 2 sine theta, if I were to graph that, so you have 1, 2, 3, 4, 5. So we have a vertical shift of 3 with an amplitude of 2, and we're going to go out to 360 degrees. So here's my 90, here's my 270. So we're going to be starting on the sinusoidal, the middle's on the sinusoidal, the end is on the sinusoidal. At 90, we'll be up here at 5, and this is 1. 270 will be down here at 1. And so this graph would look, so that one we can do without a calculator. This other one, I would recommend you go get your calculator. And oddly enough, it looks something, I'm going to do this off of memory. Oh, wait a minute. I think I have my calculator handy somewhere. Give me a second. Where did I put that calculator? Oh. Okay, so if you were to graph that one, and you'd want to do it in just regular, now rectangular form, I believe it looks something like this. It kind of comes down. We know we're going to be crossing at around 210. It seems to max around 270 and then kind of comes down again. It's kind of a weird graph. Okay, of course that's a rectangular representation. It's not going to be as a rectangle, your ellipse. And so, but you can see that around 210 and around 330, there are intersection points. Okay, so that's looking at the intersection of the polar curves. So please make sure you picked up your exploration for this as well, okay?